Hello, you are watching a breakdown video for the columnar basalt HDA that I used to make this scene in Unreal Engine 4. I'll move over to the demo map real quick to just show off the different parameters for the HDA. This is just a scene, just to demo all the different stress tests that I did with the HDA. This is just using all the same assets that I used in that last scene that I just showed you. Let me pop down an HDA really quick though, just to show you the different settings. It comes down by default in this preview setting mode, just because the full operation to get the end output is pretty heavy with all the break with the break off step and the UV unwrapping. This preview mode is just good for I don't know, it's testing out the different basic shape parameters like smoothing iterations, target size for the what do you call it, cells here. Let me set this to 0.33 and I like maybe, yeah, just set to 3. There we go. And then the extrusion settings are pretty straightforward. The bend, twist, and bend direction are all just deformers, pretty self-explanatory. Random height just adds a little bit of noise to the height of the columns here. Bevel and collider, you don't see that in the preview node. I'll pull it up preview in a second. And then division just controls the number of divisions for the columns. Let me take it off preview and show you the bidirectional and break-off stuff. Bidirectional basically just controls whether or not you want any overhangs on the geometry. It's good for like bridges or just overhang geometry, stuff like that. And then the break-offs is just taking the outside layer of columns and breaking them up a little bit, adding these overhangs just on some of the outside parts of the mesh. And then the col inner, I'll show you in this one here. The col inner just controls how much of the geometry on the inside should get deleted. Since most of this extruded geometry isn't actually seen, I just delete that in the col inner setting. Just dictates how much of that is deleted. And then last piece of functionality is that you can actually just use whatever geometry you want inside of UE4. Just move to World Outliner, wait for this to load, and start selection. Select this geometry here and use current selection. Give it a second, and there we go. And then if I wanted to have it have this overhang here, you can just turn on bidirectional and give it a second, and boom, there we go. Like I said, the preview is good for if you want a bit faster processing. See, I can just make a quick change there. There we go. Anyway, yeah, let me bring this over into Houdini and I'll show you all the steps in this HDA and hopefully explain them well. See you there. Starting out in step 1, up at the very top, there's an object merge that just imports geometry from Unreal Engine 4 into the HDA. Then there's a switch if node, just checking if there's any points inside this object merge. If there's not, then it just uses this default geometry. And that's just a sphere in a box. And then right after that, gets put into a match size. That's just to it just justifies everything above the grid line here, just so that I'm dealing all with positive values. It's a bit easier to deal with offsets for raycasts later then. And then I have a grid, which is just the size is set to the bounding box of this match size node here. So bounding box in the X direction, bounding box in the Z direction, and then it's just given a bunch of rows and columns, because in the very next node going to be using that grid to shoot a bunch of raycasts downwards onto this mesh. I do a few other raycasts, but they're pretty much all the same as this one here. Pretty much the only thing that changes is what I do with the raycast information. With this one, if a raycast misses, then it just gets put into a group to delete right away. And so that would give us a result that looks like this, with just like a silhouette basically from the top down of our reference geometry here. And that's pretty good. And then that just gets remeshed. And then I'll go over the remesh in a second. I'll go over this divide here first. It's just the default out-of-the-box divide node inside of Houdini, except I've just checked the compute dual and the avoid small angles and don't generate slivers. And the divide node is what gets the really cool, like, cellular columnar basalt-like pattern here. Still has a pretty jagged edge. We can kind of smooth out the inside by using the earlier remesh node, using the smoothing iterations, get like a more relaxed or a more messy look. I like to keep it around 3 though, and you can also move around the target size here to get different sized cells. Keep it around 0.3 though or so. And then after the divide node, we still have this jagged edge, so I've just grouped them into this. I just group the edge polygons, the edge primitives, and then just immediately delete those, which shrinks it down a little bit more, which is kind of a desirable effect anyway, just because I'm going to shoot some more rays in this very next node, and I want to make sure that they hit something, otherwise they aren't going to be extruded during the extrusion step. So this is just another raycasting downwards onto the mesh that we've imported here, and this time when we do hit something, when one of these raycasts does hit this mesh here, this mesh here, when a raycast from one of these does hit this mesh here, it actually saves that Y position into an attribute on that primitive called Z-scale, which is used later on during the extrusion phase to extrude it to that point. And also as part of that, I'm going to want the highest Z-scale that just scanned from this mesh, just using a attribute promoting to a detail using the maximum promotion method. And then the next node, I also set up another attribute that's going to be used in the extrusion node, the div scale, which just controls the number of divisions. It's just a fit with Z scale 0, max Y 0 to 1, just putting the div scale into a 0 to 1 space using what Z scale that primitive has and what the maximum Z scale is of all the primitives. And then I've also added a couple of channels here that are exposed in the HDA to add some random height to the Z scale that we scanned from this second attribute wrangle node here. And then this group node just groups the outside ring of primitives, and then the second one groups the first and the second ring of primitives. These are used later on in the break-offs and the poly reduction cleanup steps. I'll go over that when I get to those steps though. And then lastly, edge cusp just separates all these primitives into their own primitives so that they're not connected, so that later on when I have to expand these groups later on, just so when I flood fill expand these groups, they don't flood fill the entire mesh, just the columns that are about to be extruded in the next step. And that's it for step 1. Moving on to the second step, I have 2 different extrusion methods, one for the solid directional column basalt and one for the bidirectional columnar basalt. It's pretty straightforward. I just have the output front and output side on for this one, and then the bidirectional also has the output back turned on. But the interesting stuff is happening in the local control. The Z-scale and the div-scale attributes that I set up in this first step here from that raycast are used as multipliers for the distance and the divisions parameters. The Z-scale is just the stored height from the raycasts from this attribute wrangle here, and then the div scale is a 0 to 1 multiplier, so it's always going to reduce the number of divisions based off of how tall it is in relative to the maximum one. So basically it's for smaller columns there will be less divisions, for taller columns there will be more divisions. That's what the div scale multiplier does. And it's the same in this bidirectional one. There's just a few other steps that I have to do to move these primitives to their right location. Just another, I think this is the last raycast node. It just raycasts upwards this time onto the geometry and moves each point to the point that it hits on the reference geometry. And then I use my first for each loop here. I use a bunch of for each connected piece loops in this HDA, well, I'll go over those when I get to them. I'm just this one just flattens out these polygons. Oh, you can see all of them there. There we go. Flattens out all these polygons. Oh yeah, and I also do another attribute promote with the this scan here, just to get the average position of all the points after they've been moved, so that it can take away that offset from the Z scale in this after they get flattened from this for each loop. And then I just add the these ones to the extrude front group, which is a group that's also output from the extrusion node here. Yeah, one is the fronts of these primitives put in the extrusion group, and we want to bevel and do stuff to these later, and we're going to want to do the same stuff to these ones on the bottom. So I've just set them to be in the same group as the top ones here. And then they're just pumped into a switch node, just switches between bidirectional and solo directional. And then we have the group expand nodes that I talked about earlier, just flood filling all the new geometry that those primitives generated from the extrusion node. And then one quick preview material and output to preview. This is just good for seeing what'll be broken away in the breakaway node, and it's a good, fast, simple representation of what the end product will look like. And then it's just output, and that's it for step 2. Moving right along to step 3, the breakoff node. So in this one, we're going to start using the outside column in the layer 2 group set I've set up earlier. We're going to split off the first 2 layers, and we're going to put them down to this for each loop down here. And then we're going to merge them back together at the bottom. But this for each loop, this basically goes through each connected piece here. So basically each column goes through this for loop and then gets combined and put back out at the end. So I have a null node here with just basically being used as a placeholder to use the bounding box like I did back in step 1 here. I used the bounding box of this match size in this grid here. Just using that in this clip node. Clip node is basically just a node that you move the origin to where you want, and it clips everything beneath that. So it just takes, let me open this up here. It takes the bounding box of this iteration's column and clips a random spot between the top and the bottom with a few adjustments that I've put in here just to kind of move it upwards a little bit. And after that clip, we end up with a empty space at the bottom here, and then we just polyfill that with the polyfill node, and we output it with the polyfill group, because in the very next node, in the transform node, we abuse the heck out of it and just add a little bit of random transformation, add a little bit of random shear, a little bit of random rotation, so that shear gets a bunch of different angles, and then center all that around the correct pivot in the center X, center Z, and center Y, or the minimum Y, the lowest point of this column. And then the switch node is just a really easy way of controlling how many breakoffs occur. Right now it's just set to mod 2. That basically just means that every other column will have a breakoff created. If you wanted a different mod, you could just put mod 3, mod 4, or come up with a better way of doing it. This is kind of janky, I admit. And then, oh yeah, we created some more geometry, so we just want to flood fill expand the outside column layer and the outside column and the layer 2 groups, because we're going to use those more again later on in the poly reduction phase. And then group those into the extrude front group again there, just because they're new bottoms and all that. And then we put that into a merge and merge it back down to here. This switch just switches between the having breakoffs and not having breakoffs. And then to a null, and that's it for step 3. Next up, that's step 4, the UVs and the bevels. This is where it starts to get maybe a bit more complicated, but let's just jump into it. So I actually bevel the columns 2 times. This one bevels the actual columns themselves, but I really hate the seam that occurs in the UVs. No matter how you bevel this, no matter what happens, like there's going to be whether you bevel or not, there's going to be a seam there, and I wanted to try to cover that up if possible. So I actually have a second bevel that bevels it a little bit larger and then blasts away everything that's not just been beveled. So I end up with something like what's a good way to show this? Something like this. There we go. A bevel with the bevel on top of it that hides the seam that's happening on the first bevel. It's in Engine in Unreal 4. This second bevel mesh is a decal that I kind of roughens up the edge and fades off as it nears the actual column geometry. And the bevel for this is just based off of it's a reference to the value in this bevel, which is exposed. And then a bunch of unwrapping stuff. That's it for basically the beveling. The rest of this is all just unwrapping all that stuff. I'll go over the edge bevel unwrapping first here. So another 4H connected piece, pretty much the same as this 4H connected piece over here. Just using a UV project with a cylindrical projection, centering it on the X and the Z bounding box again, and then oh yeah, let me go into this mode here. So it unwraps it. It unwraps the bevel looking like this, and there's some overlapping points there. So I just put down a quick UV smooth just to smooth that a little bit. And then I want to do a bunch of stuff to this in this UV transform node. It goes from looking like this like really long rectangular piece, to looking like this. Just trying to get it more square, more closer to the fitting to the 1 to 0 UV space. But this actually squashed it down really far. Like I've rotated it, I've scaled it in Y, I've moved it there, I've changed the pivot around. But I do one more abuse to it, and I just stretch it out again to look like this, just so that we get nice square texel density space. I'll admit this is really janky. I'm sure there's a better way of doing this, better way of unwrapping this, but it seems to work well enough in Engine. And once we get all of them together, it looks like that. Kind of a mess. And then just, it goes down here. I group this outer edge here just for vertex coloring later on, and then I put a UV quick shade and merge it back together. And then for this one over here, it's pretty similar to this unwrap. Cylindrical, centering on X, centering on Z. Oh, don't need to change that. And then the UV transform doesn't quite abuse it quite as much. For this one, it just moves it into this 0 to 1 space here. Still overextends here. And then one more UV projection, just getting the caps in the bottoms of the columnar basalt columns. And then here I just copy UV set 0 into UV set 1, just so I can hold onto this in Engine if I want to put any like noise or decal or whatever over top of this. Nice square UV space to do that in. And then in this another 4H connected piece loop, or no, this is 4H connected piece. This might just be for loop. I don't remember. Anyway, oh yeah, 4H point piece. Okay, yeah. This is just to randomize the UVs. This one just moves a UV to random amount upwards and to the side, and this one randomizes the position and the rotation. So we end up something that looks like, if I turn on randomize UV, something that looks like that, or something that looks like that. Depending on what material or textures are being used, might be a desirable effect. Then it gets quick shade and then merge back together with these seam hiding poly meshes. And yeah, that's it for step 4. Moving on to step 5, the vertex colors. This uses another 4H connected piece, just creates a green gradient. Let me, there we go. Creates a green gradient, top-down green gradient over everything. Good for it's used in UE4 in the material, just to give a nice top-down gradient for each of the columns. And then I also do a calculated occlusion. I've turned down the number of rays way lower, just because it doesn't need all that many rays to get an okay look. And then I just extract that AO and put it into the blue channel, and then I add opacity to the this is where the group 4 outer group comes in. I just color the edges blue, which I'll use for opacity in the decal material for these bevel end caps. And that's it for group step 5. Really quick one. Moving on to second to last step, the cleanup. This is where I take care of the really bad poly count that is in this so far. Like in something like this, it's not so bad, but really, really, really big columnar basalt formations, there ends up being a ton of unnecessary geometry happening on the inside, which is why I've been grouping up the outside columns in earlier steps. Because you pretty much only need these outside 2 for the side view of any columnar basalt. You only need to see the breakoffs in there, and then the layer behind the breakoffs, and then everything else is almost never seen except for the very top division of each one of those columns. So this step just deletes everything except for the visible columns on the inside part of the columnar basalt mesh. Again, there's 2 different versions for deleting. There's one for solid direction, one for bidirectional, because the bidirectional, there's always stuff on the top and the bottom. With the solar directional, you wouldn't really ever see it from the bottom, so you can there are different methods. Anyways, just delete node with using the bounding volume method. With this solar directional one, it's just setting the size to, I don't know, something really, really big, and the X and the Z, and then the Y size is just set to the bounding box for from this node here. Oh yeah, and this attribute wrangle node is just basically a placeholder for a delete channel or delete range channel that's exposed in the HDA down here. So yeah, this delete node's bounding box volume is set to the bounding box of this mesh here, or not that mesh, of this whole mesh here, and then it's multiplied by the delete range attribute or channel from this node here. So when it's multiplied by, let me open this up here. So basically, when it's set to be multiplied by 1, we have it deleting absolutely everything in the mesh. Oh, let me set this to bidirectional. There we go. So delete that. When we have the delete range set to 1, then it's multiplying this bounding box by 1, and we're deleting everything. If we just move it down a little bit, then we end up with, well, let me show the whole thing. There we go. If we have 1, we're deleting everything. If we multiply it by less than 1, then we start to get more and more and more of the inside mesh here. I like to keep it around 0.95, just to get the very tops. And then the bidirectional one is pretty much the exact same thing. We just sent the center to be in the middle of each column, and we set the bounding box size like that. Yeah, pretty much the same thing, just shrinks it from the center rather than from the origin down to the bottom here. And then a switch between the two, whether it's bidirectional or solar directional, and then merge back together with the two groups from earlier, and then done. That's it for step 6. Then moving on to the final step. This one's another really, really quick one, just importing the last one from here and the preview mesh from way back in step 2 here. Importing both those, putting in a switch that switches between preview mesh or not. There we go, yeah, preview mesh, yeah. And then just a couple quick deformers, 2 bends, pretty much the same thing. One's just bending from the top, the other one's bending from the bottom. I could also just expose the capture direction here, but for the uses I found for this, I've only really ever had the bend from the top or from the bottom. Don't really need to do any side bends. And then another switch, the switch between the reverse bend or the regular bend. Then just deleting some unused groups, putting it through null node, and outputting. That's the entire HDA.